play games, or even send a simple text, there's one crucial component inside your computer making it all happen: the CPU, or Central Processing Unit. But have you ever wondered how this tiny chip works its magic? Let's break it down. A CPU is often called the brain of your computer. It performs all the instructions needed to run programs. Its work can be summarized in three key steps: fetch, decode, and execute. The first step is fetching. The CPU retrieves instructions from the computer's memory. These instructions are stored in binary, a series of ones and zeros. Imagine it like reading a recipe before cooking. For example, if you open a web browser, the CPU fetches the instructions for displaying the browser on your screen. Next comes decoding. This is where the control unit inside the CPU translates the fetched instructions into a language the computer understands. Think of it like interpreting a recipe: what ingredients you need and what steps to follow. If the instruction is to add two numbers, the CPU will identify it as a math operation. Finally, there's execution. The arithmetic logic unit, or ALU, takes over here. It performs calculations or logical operations based on the decoded instructions. This is where the actual work happens. For instance, in a gaming scenario, the ALU calculates the physics of a jumping character or processes enemy movements. But the CPU doesn't work alone. It relies on registers to store small amounts of data temporarily and uses cache memory for quick access to frequently used information. These help speed things up significantly. Modern CPUs also feature multiple cores, allowing them to perform multiple tasks simultaneously, which is essential for multitasking. Another critical component is the control unit, which acts as the conductor of an orchestra, ensuring that all parts of the CPU work together seamlessly. It coordinates the flow of data between the memory, ALU, and input or output devices. The CPU's speed is determined by its clock cycle, how many instructions it can process in a second. Modern CPUs can handle billions of cycles per second, making them incredibly fast. Over time, advancements in technology have introduced smaller transistors and improved in architectures, enabling CPUs to be both powerful and energy efficient. Beyond speed, the efficiency of a CPU depends on features like pipelining, which allows the CPU to work on multiple instructions at different stages of completion. It's like an assembly line where tasks are broken into smaller or more manageable steps. In essence, the CPU is like the ultimate multitasker, fetching, decoding, and executing millions of instructions per second, all while coordinating with other components. It's the powerhouse behind every digital task you perform. CPUs, or Central Processing Units, are fundamental to modern computing. They serve as the core of every computer system, and their development over time has been integral to advancing technology. Reflecting on this journey provides insight into how computing power has shaped the modern world. The 1960s marked the beginning of a significant shift with the invention of integrated circuits, allowing multiple transistors to be placed onto a single chip. This breakthrough led to the release of the Intel 4004 in 1971, the first commercial CPU. Despite its limitations by today's standards, it was capable of executing over 46,000 instructions per second, representing a massive leap in efficiency and compactness compared to earlier machines like ENIAC, which could handle fewer instructions and required an entire room to operate. At its core, the CPU operates by fetching, decoding, and executing instructions. Early processors worked with simple 4-bit architectures, allowing them to process smaller amounts of data. Today, CPUs typically use 64-bit architectures which significantly expand their ability to handle larger and more complex tasks. Alongside this growth, improvements like memory caching addressed bottlenecks in system performance, such as slow data retrieval from RAM. This balance between processing power and memory efficiency has remained a key area of innovation. Instruction sets have also evolved to meet growing demands. In earlier CPUs, instructions were basic, handling simple operations like arithmetic and logic. Over time, instruction sets expanded to support complex applications, enabling CPUs to handle workloads ranging from data processing to artificial intelligence. These changes reflect not just an improvement in speed but a transformation in functionality. In modern CPUs, the scale of progress is evident. For example, processors like Intel's Core i9 are capable of executing over 80 billion instructions per second. However, the focus has shifted beyond speed to include power and efficiency and adaptability. The fact that today's smartphones can outperform earlier desktop computers highlights how far this technology has come. As the limits of traditional silicon-based processors are approached, future developments may include quantum computing or entirely new architectures. This evolution made it clear that CPUs represent more than just technological advancement. They are a testament to decades of engineering and problem solving. Understanding their progression offers a valuable perspective on how computing power has shaped and will continue to influence modern society. In 1972, Intel introduced a revolutionary piece of technology, the Intel 8008 microprocessor. This was an 8-bit processor that marked a dramatic shift in the landscape of computing. Prior to this, most computers relied on 4-bit processors, which were limited in both speed and functionality. The Intel 8008, however, was designed to process 8 bits of data at a time, doubling the processing power and enabling a range of new applications and possibilities. At the time, Intel was just beginning to establish itself as a leader in the microprocessor industry. The 8008 had a clock speed ranging from 500 to 800 kHz, which, while modest by today's standards, was a significant step forward for its era. This allowed the 8008 to process instructions more quickly and efficiently than its predecessors. The processor could address up to 16 kilobytes of memory, a considerable improvement over previous processors that could only handle much smaller amounts. The architecture of the Intel 8008 was also notable. It featured a set of 3 general-purpose registers which were used to store temporary data during computations. This made the processor more flexible and capable of handling a variety of tasks. The 8008 also supported indirect addressing, a feature that allowed the processor to access memory locations via pointers rather than directly referencing them. This was a crucial advancement because it made programming more efficient and opened up the possibility for more complex and dynamic software applications. One of the major applications of the 8008 was in early personal computers. For instance, the Tandy TRS-80, released in 1977, used the 8008 processor as the heart of its system. The Mark 8, another early personal computer, also utilized the Intel 8008. These systems, powered by the 8008, helped lay the foundation for the rise of personal computing in the late 1970s and early 1980s. Although the 8008 was a significant step forward, its successor, the Intel 8080, was where the real breakthrough occurred. The 8080 was an evolution of the 8008 and introduced a number of improvements, including a faster clock speed, greater memory addressing capabilities, and support for more advanced instructions. The 8080 became the processor of choice for many of the earliest personal computers, including the Altair 8800, which is widely credited with sparkling the personal computer revolution. However, the 8008 should not be underestimated in its own right. While it was overshadowed by the 8080 in terms of commercial success, the 8008 was instrumental in proving the viability of microprocessors as the central component of a personal computer. It demonstrated that a small, affordable chip could perform tasks that were once reserved for large, expensive machines. This idea would become the cornerstone of the personal computing revolution, and it all began with the 8008. In terms of design, the Intel 8008 was based on a relatively simple and efficient instruction set, which helped reduce costs and made the processor accessible to a wide range of industries. It wasn't just for personal computers. The 8008 found applications in other fields, including industrial automation, consumer electronics, and communication systems. This was a testament to its versatility and ability to power a wide variety of devices. The release of the 8008 also had a profound impact on the development of software. The introduction of indirect addressing, in particular, opened up new possibilities for software developers. They could now write more complex programs that could dynamically allocate memory based on the needs of the task at hand, making software development more efficient and powerful. This, in turn, contributed to the rapid expansion of software applications that could run on microprocessor-based systems. Looking at the broader context, the Intel 8008 was part of a larger trend in computing during the 1970s. The shift from large, centralized mainframe computers to smaller, decentralized systems that could be used by individuals and small businesses. Before microprocessors like the 8008, computers were enormous, expensive machines that required specialized knowledge to operate. With the advent of the 8008 and similar processors, computers became more affordable and accessible, allowing anyone with a little technical know-how to build their own system. By the time the 8008 had been succeeded by the 8080, the computing world was on the brink of a revolution. The 8080 would go on to power some of the most iconic early personal computers, such as the Altair 8800 and the IMSI 8080. But it's important to remember that these innovations were built on the foundation laid by the Intel 8008. Without the 8008, the rapid development of personal computing in the 1970s and 1980s might not have been possible. The evolution of CPU processing power is one of the most remarkable stories in technology, and modern operating systems have played a crucial role in shaping that journey. In the earliest days of computing, there were no operating systems as we know them today. Computers were manually operated, with users inputting specific instructions for every task. It was time-consuming, inefficient, and far from user-friendly. The introduction of operating systems changed everything. Early systems like MS-DOS provided a way to manage hardware resources, streamline processes, and enable basic multitasking. They paved the way for a more accessible and efficient computing by creating a structured environment for running programs and managing the interaction between the CPU and the rest of the system. As time progressed, graphical user interfaces like Windows and Mac OS emerged. These systems revolutionized the way people interacted with computers. They weren't just about aesthetics. They brought major advancements in multitasking, memory management, and resource allocation. They allowed users to switch between tasks seamlessly while ensuring that the CPU could handle the workload effectively. Today, modern operating systems have taken things to an entirely new level. They're no longer just limited to managing individual machines. They support distributed computing, power cloud-based platforms, and utilize the full potential of multi-core CPUs. Systems like Linux, Windows 11, Mac OS, and even mobile operating systems like Android and iOS are designed to handle massive amounts of data, run complex applications, and deliver seamless performance. The evolution of operating systems has been driven by the need to make technology more efficient, versatile, and accessible. They've transformed how we interact with machines and unlocked the true potential of CPUs. As we look to the future with innovations in artificial intelligence, cloud computing, and even quantum technologies, operating systems will continue to adapt and redefine what's possible, shaping the next generation of computing. In 1981, Microsoft made a pivotal hire, Charles Simonyi, a former Xerox programmer who would go on to shape the future of personal productivity applications. 7 years prior, Simonyi had developed Bravo, the first graphical user interface or GUI word processor for the Xerox Alto. His groundbreaking work laid the foundation for what would become Microsoft Word. Paired with another former Xerox engineer, Richard Brody, the team produced Multi-Tool Word, Microsoft's first word processor. Initially released for the Xenix operating system, Microsoft Word would eventually reach MS-DOS in 1983. The program's inclusion in the November 1983 issue of PC World as a free demo marked a significant milestone, as it was the first software bundled with the magazine. At the time, Microsoft Word offered a mouse-driven user experience, a rarity among DOS programs. However, it lacked features like font rendering, making it less competitive compared to WordStar, the dominant word processor. Yet, despite its simplicity, the entire package of the first Microsoft Word version took up only 150 kilobytes. Fast forward to today, and the modern version of Microsoft Word now demands at least 4 gigabytes of disk space and 2 gigabytes of memory to even run. This rapid expansion of software from basic text-based tools to complex, visually rich applications drove the need for more powerful processors capable of handling larger memory sizes and faster computing speeds. The 1980s and 90s saw a shift toward 32-bit processing architecture, an evolution that would eventually redefine the computing world. While 32-bit architectures had existed since the late 1940s, they were primarily seen in mainframes. At the desktop level, only a few processors had full 32-bit capabilities, often operating in a hybrid form. For example, Motorola's 68K series used a 16-bit data bus combined with 32-bit registers. However, by the mid-1980s, the demand for more processing power led to the mainstream adoption of true 32-bit processors. In 1982, National Semiconductor released its 32K series, starting with the 3216, a true 32-bit microprocessor. However, issues like design bugs and slow speeds hindered its adoption. By 1984, Motorola introduced the 6820, a true 32-bit processor that became popular in systems like the Apple Macintosh II and the Commodore Amiga 1200. Despite the advancements, the 6820 lacked integrated memory management, which would later be addressed with the 6830. Meanwhile, Intel was making strides in 32-bit architecture with the 8386 processor released in 1985. This marked a significant milestone in the x86 architecture. The 386 introduced 32-bit internal and external buses, a powerful memory management unit, and backward compatibility with previous Intel processors. By 1986, Intel's 8386 became the first mainstream 32-bit processor to hit the market, offering significant performance improvements over its predecessors. The 386 processor also brought new memory management capabilities, including a virtual 8086 mode, which allowed for the encapsulation of multiple real-mode environments within a single protected mode. These advancements laid the foundation for modern operating systems, as the 386 flat memory model and virtual addressing allowed programs to be loaded into memory fragments, optimizing memory usage across the system. However, as processors became more powerful, a critical bottleneck emerged: memory access. While the CPU speeds rapidly outpaced memory speeds, a solution was needed to avoid stalling the instruction cycle. Enter pipelining, a design that divides the instruction cycle into sequential stages, allowing for parallel processing. This concept, initially seen in supercomputers, made its way into mainstream CPUs in the 1980s. With pipelining, instructions could be processed simultaneously across different stages, improving throughput and increasing the CPU's clock speed efficiency. However, pipelining introduced challenges like data hazards when one instruction depends on the data from another instruction ahead of it in the pipeline. To manage this, techniques like pipeline bubbling and operand forwarding were introduced, allowing the pipeline to maintain flow even during stalls. More advanced processors implemented out-of-order execution, which further optimized the processing flow during hazards. While pipelining improved efficiency, another issue emerged: memory access speed. To address this, CPUs started integrating caches, small, high-speed memory buffers that store frequently accessed data to reduce delays. Caching helped to alleviate the bottleneck created by slower memory access, and by the 1990s, multi-layered cache systems were implemented, including level 1, 2, and sometimes even level 3 caches. Early CPU caches were simple, like the 68020's 256-byte instruction cache, but as processor speeds increased, cache complexity grew. The 386, for example, had no internal cache but could be augmented with up to 64 kilobytes of external cache. By the time of the 486, on-die caches became the norm. These cache systems were designed to optimize memory access, with algorithms like least recently used, or LRU, helping to determine which data to keep in the cache. As CPUs became more complex, memory management and cache systems became increasingly sophisticated, enabling higher processing speeds. Techniques like direct memory access, or DMA, allowed devices to access memory independently of the CPU, improving system efficiency. Meanwhile, multi-core processors and advanced cache systems helped optimize performance in more complex computing environments. By the late 1990s, processors had evolved to incorporate even more advanced techniques such as superscalar pipelining, which allowed multiple instruction paths to be processed in parallel. This helped to further reduce bottlenecks and maximize CPU throughput, laying the groundwork for the high-performance processors we use today. The evolution of CPU processing power, from the humble beginnings of 8-bit processors to the sophisticated 32-bit systems of the 1980s and 90s, paved the way for the modern computing era. With the integration of pipelining, caching, and memory management innovations, processors became capable of handling more complex tasks and running more powerful applications, setting the stage for the next generation of computing. As we look back, we can see how these innovations, small at the time, contributed to the massive leap in performance that defines today's computers. With each new generation of processors, we continue to push the boundaries of what's possible in computing, making the world of technology ever more powerful and efficient. The graphics processing unit or GPU has significantly evolved from its early days as a specialized graphics accelerator to a powerful parallel processor that drives many aspects of modern computing. Initially, the GPU's role was focused on rendering graphics for video games, offering dedicated hardware to efficiently process and display images. Today, however, GPUs have found applications far beyond graphics, becoming integral to fields such as machine learning, scientific simulations, and even cryptocurrency mining. When I first started learning about GPUs, I mainly associated them with gaming. I thought they were just the hardware responsible for making games look better or running smoothly. However, I've come to realize that the impact of GPUs is far broader. A modern GPU is capable of executing thousands of threads simultaneously, making it an essential tool not only for rendering images but also for tasks that require massive parallel processing like training AI models. The architecture of a GPU is fundamentally different from that of a CPU. While the CPU focuses on single-threaded performance to handle tasks that require fast, sequential processing, the GPU excels in performing many tasks simultaneously. This parallelism is why GPUs are so well suited for complex computations, particularly those that involve large amounts of data such as deep learning and data analytics. One of the most impressive advancements in GPU technology is its role in machine learning. The rise of AI and deep learning has made GPUs an indispensable part of modern computing. With their ability to handle parallel processing, GPUs have greatly accelerated the training of neural networks, enabling breakthroughs in fields like natural language processing, computer vision, and even autonomous driving. It's fascinating to see how GPUs are helping shape the future of technology in ways that I hadn't anticipated when I first learned about them. While GPUs have undoubtedly transformed many industries, they also come with challenges. The sheer computational power of GPUs comes with high energy consumption and heat generation, which is something to consider when designing systems that rely on them. Additionally, as GPUs are now in high demand for a variety of tasks beyond gaming, supply chain issues and price hikes have also become a concern for consumers and businesses alike. Overall, reflecting on the evolution and current capabilities of GPUs, I realized just how far technology has come and how much further it can go. The GPU is not just a tool for gaming or graphics anymore. It's an essential building block of the future of computing. Whether it's powering AI research or enabling the next generation of video games, the GPU is undeniably at the heart of innovation in modern technology. The SAP1 or Simple as Possible 1 architecture is a basic yet pivotal concept in understanding how computers process instructions at a low level. When I first encountered SAP1 operations, I was introduced to the fundamental building blocks of a computer's operation. SAP1 is often used in educational settings to help students grasp how a computer executes instructions through its various components such as registers, the arithmetic logic unit or ALU, and memory. What struck me most about SAP1 operations was the simplicity of the system and how it mimics the core functions of more complex systems. SAP1 provides a clear, step-by-step sequence that demonstrates how data moves between the various components of the computer. The operations within the SAP1 architecture, including the instruction cycle, instruction fetch, decoding, and execution, allowed me to understand the flow of data within the computer more clearly. The first operation in the SAP1 cycle is fetching an instruction from memory. This is where the program counter plays an essential role. The instruction fetch phase helps set the stage for the execution process. From there, the instruction is decoded and the necessary operations are determined. The ALU, for instance, performs basic arithmetic or logical operations as per the instruction, while registers store intermediate values. What I found fascinating about SAP1 was how the machine language instructions are directly tied to the hardware operations. It's intriguing to think that even today, the basic principles of instruction cycles in processors are rooted in concepts introduced by designs like SAP1. It was a great way to understand the practical application of theory in computer architecture. Even though SAP1 is simplistic, it mirrors the general idea of how complex microprocessors execute instructions, just on a much grander scale. Another key takeaway from the topic was the concept of control lines, which help orchestrate the operations of SAP1. The control unit is responsible for generating control signals that direct the movement of data between registers, memory, and the ALU. Understanding this was a light bulb moment for me. I could finally connect the dots between the abstract theoretical concepts I had learned in class and the real-world application in processors and other computing devices. While learning about SAP1 operations, I realized the importance of each step in the instruction cycle. If any of these operations is misunderstood or not implemented correctly, the whole instruction cycle would fail. This highlights how crucial it is to have a well-coordinated system that can process instructions sequentially and accurately. SAP1 operations also introduced me to the idea of sequential and parallel processing. The system executes one instruction at a time, but it's this sequence of operations that allows the computer to process complex tasks. This concept is foundational for understanding how more advanced processors and systems handle multiple tasks and resources simultaneously. Looking back at my study of SAP1 operations, I now see it as a great foundational exercise. It's a great entry point into the world of computer architecture. The SAP1 system may seem simplistic compared to modern microprocessors, but its operations are a crucial step toward understanding the complexities of today's computers. From here, I feel better equipped to explore more complex systems such as RISC and CISC, which build upon the principles that SAP1 introduced. Ultimately, learning about SAP1 operations has given me an appreciation for the fundamental principles that drive the more advanced computing systems we rely on today. As I continue my studies, I know that understanding how basic systems like SAP1 work will allow me to better grasp the advancements in modern computer architecture. The SAP1, being a basic microprocessor, uses machine language and assembly-like instructions that directly map to the operations performed by the hardware. This made it clear to me how closely programming is linked to the architecture of the system it runs on. Each instruction executed in SAP1 corresponds to specific hardware-level actions like moving data between registers, performing arithmetic and logic operations in the ALU, or updating memory. This hands-on approach to understanding how a program runs inside the computer gave me a more tangible understanding of what happens when we run a program. The process of programming the SAP-1 starts with writing simple machine-level instructions that are understood by the processor's instruction set. These instructions are quite minimalistic but show the core functions of a computer: loading values into registers, performing operations, and storing results in memory. I was surprised by how each action in the instruction cycle, fetching, decoding, and executing, plays a pivotal role in executing a program. It made me realize how even simple tasks in high-level programming languages are supported by these low-level operations. One of the most interesting aspects of SAP-1 programming is how it forces a more direct connection between software and hardware. When programming in SAP-1, I couldn't rely on higher-level abstractions that modern languages provide. Everything had to be done step by step, and the instructions had to be written in such a way that they made the most of the limited resources the system had to offer. This hands-on approach to programming taught me how every detail in the code matters, as there's no room for unnecessary overhead. Another key takeaway from programming the SAP-1 is the concept of memory addresses and the role of the program counter. The PC points to the next instruction to be executed, and I had to carefully manage how instructions were loaded and executed. This taught me the importance of managing program flow at the hardware level. It was eye-opening to see how something as simple as moving data from one register to another can have a profound impact on the overall execution of the program. Learning to work with SAP-1 also brought to light the importance of control signals. These signals are what guide the processor through the execution of instructions. Understanding how control signals are generated and how they influence the operation of the registers and ALU deepened my understanding of how CPUs operate. It was a valuable experience that made me more aware of how much is happening behind the scenes when a program runs on modern computers. Though SAP-1 is limited in terms of functionality and resources, this limitation was what made the learning process so effective. The simplicity of the architecture allowed me to focus on core programming concepts without the complexity of modern processors. It showed me how basic instructions like loading data into registers, performing operations, and storing results all come together to form the foundation of computation. SAP-1 programming also made me think about the evolution of processors. While SAP-1's instruction set and architecture are minimal, they laid the groundwork for more advanced systems that would come later. The principles of data movement, control flow, and execution that SAP-1 introduced can be seen in today's processors, albeit at a much larger scale. Modern programming languages and high-level abstractions have made it easier to develop software, but understanding the basic building blocks of how those programs run is essential for becoming a well-rounded programmer. SAP-1 may be a simple system, but the knowledge I gained from working with it is anything but simple. It's a fundamental lesson in understanding the relationship between software and hardware, and it will continue to serve as a solid foundation for more advanced topics in computer architecture and programming.